meaning when you hear a fluid pour, you kind of have an idea of what the viscosity is of that fluid. So some influential scientists that have made an impact on viscosity are Isaac Newton and Albert Einstein. And Isaac Newton described how normal fluids and liquids behaved, and he observed that they have a constant viscosity. And he, or we call these normal fluids, Newtonian fluids. And what I'll point out later on in the talk is that this was only part of the characteristics of fluid. There's also fluids that don't behave in this way. Albert Einstein contributed molecular size through the use of intrinsic viscosity. And in molecular size, you use intrinsic viscosity to find the hydrodynamic radius of the molecules within the sample. And so what is viscosity? Viscosity in its simplest definition is resistance to flow. However, any fluid that flows has viscosity. For example, in the cannabis industry, terpenes flow very easily, so obviously they have much lower viscosity compared to distillates, which are very high in viscosity and don't flow very easily. And then when you mix terpenes and distillates, you get a blend, and that's usually somewhere in between. And so what's happening at a molecular level basically is friction between the molecules. And this intermolecular force resists shearing motion or movement of the molecules, which is a simple way of seeing how viscosity can be very high. For example, in very viscous fluids, the molecules tend to like to stay connected, and that movement is very difficult. However, in low viscosity samples like water, the water molecules can move freely over each other, so the friction is actually quite very low. This is an example of THC as well as CBD. And so getting into a little bit more about the fluid elements in motion, an experiment that is very common in viscosity is the parallel plate experiment, where you have a plate that is stationary and a plate that moves. And so this is a classic example of how viscosity is measured. And so as the plate is moved, the fluid resists that movement, and we could take those forces and use those forces to calculate viscosity. And so there are two parameters that you need to measure true viscosity, and that is shear stress and that's shear rate. Shear stress is force per unit area, and shear rate is velocity divided by the height of the gap. And so with the ability to calculate shear stress and shear rate, you can calculate viscosity. Viscosity isn't just a number. I want to point out that it's also a reflection of the molecular interactions, and it reflects molecular level behavior, basically. And so with this, you can get an idea of the size of the molecules, the shape, how they interact, as well as the microstructure. And so as I mentioned earlier, Sir Isaac Newton noticed that viscosity remains constant, but we know now that there's actually another part of that, and that is a viscosity dependent on shear rate, which is considered non-Newtonian. And in simple terms, what that means is as a shear is put or imparted onto a fluid, then the viscosity changes with what we call shear rate. And so for non-Newtonian fluids, as the shear rate increases, the viscosity changes, and you can either have shear thickening or shear thinning. However, if you have a fluid that does not show this change in viscosity as a function of shear rate, the viscosity stays constant, then that is a Newtonian fluid. And so we say that Newtonian fluids have a viscosity that is constant and is independent of shear. Non-Newtonian fluids, viscosity is not constant and viscosity is dependent on shear. And so getting into a little bit more detail of Newtonian and non-Newtonian interactions at the molecular level, we can look at section A here. And in a static state, the molecules are random. And however, as the shear rate is increasing, what can happen is the molecules begin to line up. And in the case of shear thinning samples or fluids, this lining up allows the different molecules to basically slide over each other. And this sliding action is reflected as shear thinning. However, shear thickening, you have cluster formation. And so you may have some areas that are lined up, but then the molecular interaction between the molecules can cause a cluster, which you can think of it as kind of like a roadblock. And so this actually prevents the different molecules from sliding over each other, and that is reflected as shear thickening. And so some common Newtonian fluids are water, gasoline, and alcohol. Shear thinning, you see that in cannabis oil, paints, whole blood. And in shear thickening, you see that in cornstarch and water or sand and water. So now I'll get into the different types of viscometers that are on the market. And so some of the first viscometers are rotational systems. Oops, you know what? Sorry about that. I skipped over the gravity viscometers. The gravity viscometers are actually one of the first viscometers developed. And these are U-tube viscometers. Oswalt's are also Ubelodi tubes. And these are gravity driven. And so what you do, you basically fill up the tube with your sample. You have a timer and you see how long it takes to go from point C to point D, and then you multiply that by a constant, which is a defined parameter that is indicative of the tube dimensions, and with that you get viscosity. Another gravity-driven viscometer is called the falling ball. And basically what happens with this type of viscometer is your fluid fills this cylinder and then a ball is dropped. And then the ball or the sphere has a known weight and size, and it is allowed to reach terminal velocity. And with this terminal velocity, you're able to calculate the frictional force or Stokes drag, and from there you can calculate dynamic viscosity. So the next evolution of viscometers are rotational systems. Sorry about that. And these are, so these type of viscometers, there's two types. There is a spindle type and a cone and plate. However, they both share the same type of technology where you have a spinning element within a sample. And so the spindle type viscometers rotate in this fluid. The fluid is basically turned, and the torque is converted into reference viscosity. And so reference viscosity is a little bit different than true or absolute viscosity, in the sense that reference viscosity, the viscosity is compared to a known standard. The next evolution of rotational systems is the cone and plate. And with the cone and plate, you are actually able to get true viscosity. And how that is done is by knowing the dimensions of the cone and plate and how much interaction there is with the fluid. With spindle-based systems, the geometry isn't exactly known, and because of that, you're not able to accurately estimate shear rate. And in the previous slide that I had, in order to calculate absolute or true viscosity, you need to know the shear rate. With cone and plates, you're able to precisely calculate shear rate. And so with cone and plate, you have the ability to calculate true viscosity, which is much different than referenced. And so the next evolution is viscometers that are Vrock, viscometer, rheometer on a chip. And that is a technology that Riosense developed. And some of the advantages of Vrock technology is it is based off of microfluidics and MEMS. And so with this technology, sample volume is much less because of microfluidics. And MEMS allows for a flow-through design, and so you could actually reach higher shear rates. And so how our technology, our Vrock technology works is the fluid is pumped into the flow channel, and embedded within the flow channel are pressure sensors. And so the pressure drop as the fluid is flowing is proportional to shear stress. We can calculate, or we can control shear rate by use of a positive displacement pump. And we know the exact dimensions of the flow field. And with those two parameters, we have shear rate. And so we can calculate true or absolute viscosity by measuring the pressure drop, which is proportional to shear stress, divided by shear rate, and that gives us absolute viscosity. Now I'd like to talk about the temperature testing, is that it is greatly influenced by temperature. And so here we have two samples, sample 1 and sample 2. And at 40 degrees, the viscosity is 8,000 for sample 1, and for sample 2, it's about just under 6,000 centipoi. And so for reference, honey is 10,000 centipoi. So this is just a bit less viscous than honey. However, if you notice going from 40 to 45 degrees, the viscosity changes quite dramatically. It basically goes down more than half, going from 8,000 to about 3,500 for sample 1. And sample 2, you're going from about 5,600 to 2,700. And we see the same type of decrease as we're increasing in temperature. And so why does this matter? So it matters in a few different ways. When you're formulating your cannabis oil, you want to understand what viscosity is as it's getting closer and closer to combustion. Some negative impacts of not knowing the viscosity as it's getting higher and higher in temperature are you can have leaks, you can have insufficient burning, or you can have insufficient vaporization, or you could have burning, which are all very negative in terms of the customer experience. And so we also, through our testing, see that cannabis oil is non-Newtonian. Again, non-Newtonian meaning it is dependent, the viscosity is dependent on shear rate. And with cannabis oil, we see that it is shear thinning. Here we're taking shear rates going from 10 inverse seconds all the way up to over 1,000. And at low shear rates, the viscosity at 25 degrees C is around 40, just under 44,000. However, it decreases quite dramatically as your shear rates are increasing, and a little over 1,000 inverse seconds, the viscosity dropped to just a little over 2,000. So the impact of additives and viscosity on distillates is actually quite dramatic. Some of the work that we've done, we've seen nearly a 10-fold difference in viscosity of blends to distillates. Blends also exhibit non-Newtonian characteristics where shear rate influences viscosity. Temperature also has a large influence, and as the temperature is increasing, we see that viscosity begins to go lower and lower with increasing shear rate, nearly the viscosity of water. One thing I'd like to point out too is that hardware for vaping is highly dependent on viscosity. And so if you are, if your oils are blends or distillates, you need to take into account the different viscosities that you can have and how the hardware must match the viscosity of your product. Otherwise, you can have leaks and you can have poor combustion, you can have burning, which are all very negative in terms of the customer experience. So this is a comparison of distillates and blends. And so where I'd like to focus your attention is at around 40 degrees C. And so with the blend that we tested at 40 degrees C, the viscosity was approximately, I'd say around 2,500 centipoi. But at 40 C with the distillates, these are distillates, the viscosity is much higher. It's for sample 1 is about 8,000, and for sample 2 it's about 5,600. So there's a huge difference in viscosity. And again, this is something that you need to consider when you are matching your hardware to your product. And so now what I'd like to talk about is fluid flow. And if you recall earlier in the talk, I spoke about how fluids can be Newtonian or non-Newtonian. And so just a reminder, non-Newtonian fluids like cannabis oil, viscosity changes as the fluid flows. Another way of looking at it is once the fluid begins to flow, there's a certain amount of force that's put upon the oil. And so we see these forces also in the hardware used for vaping. And where those forces occur are at these pores. And so you can imagine as the cannabis oil is flowing into these pores, it's getting squeezed down into this opening, and that's a force or a shear force. And what that'll do is it'll cause the viscosity of the cannabis oil to decrease. And so when you're formulating your cannabis oil, understanding the pore size and how that'll impact your oil is very important. Again, without doing the analysis of your cannabis oil and understanding how your oil is changing with the shearing impact, this will have a big influence on the vaporization of the oil as well as leaks. And finally, I'd like to go over the key points of my talk. Viscosity is a reflection of what is happening at the molecular level. It gives you insight as to what is happening with the molecules as they interact with each other. Understanding viscosity is really important if you are adding terpenes to your distillates, because that will change the viscosity greatly. It's also very important to understand viscosity and matching that to your hardware. Product performance is directly related to viscosity, and if you're not doing the viscosity work up front, that could lead to poor customer experience, leading to poor brand identity, loss of revenue, and that would negatively impact the bottom line. Some examples of negative customer experiences are no vaporization, burning, or actually leaks. So that's all I have for today's webinar. Thank you very much for your time, and please reach out if you have any questions. Thank you.